Hi, I'm Hassan, the lecturer here at the Institute of Medical Education, and today we're going to take a look at solutions to Section 3 of ACER's GAMSAT Green Booklet, Practice Test 1, specifically Unit 33, questions 102 to 103. And we're going to take a look at thermodynamics and Gibbs free energy, enthalpy, and entropy. So you're being provided the equation for Gibbs free energy in the unit, and we have to answer a couple of questions relating to it. So just before we tackle this unit, it's important we have some foundational knowledge of some thermodynamic points. So remember, exothermic reactions, they release heat. So if the change in our enthalpy represents our internal energy, that means if we're losing energy, we're losing internal energy, and our enthalpy is going to be less than zero. So if we take a look at the other side of the coin, for endothermic reactions, we're adding heat to the system. So that means we're going to increase the enthalpy, so the internal energy in the system, so it's going to be greater than zero. So when we're looking at Gibbs free energy, it's telling us whether the reaction is going to be spontaneous or not. So if I just quickly draw the Gibbs free energy equation here, you can see that entropy, remember, entropy represents disorder. So if you have an entropy that's greater than zero, it's going to be a more disordered system, whereas entropy less than zero are going to be more ordered. So we'll go through that in the next couple of questions about how we can manipulate that. But you can see that for a reaction to be spontaneous, so for, say, entropy to be disordered, to be spontaneous, it makes sense that G, so change in G, has to be less than zero. Because if your entropy value here, or the change in entropy, is very high, that means it's going to be very spontaneous, it's going to be very disordered, it's more likely to occur, which means this negative value is going to make this value very high. And obviously, if you have a fixed enthalpy value, let's say it's a low value, therefore it's going to be spontaneous. But there's obviously going to be instances where it could be a negative enthalpy, positive enthalpy, negative entropy, positive entropy. So you can't just make inferences like that from the equation. But one important thing to note is temperature is very, very, it plays a big role in whether or not the reaction is going to be spontaneous or not spontaneous. So if we take a quick look here, if the delta G, the Gibbs free energy, is less than zero, the reaction will be spontaneous and it'll proceed in a forward direction to form more products. Whereas the opposite is seen here. It won't be spontaneous, and it'll go in the reverse direction to make more starting materials. So just take note here as well of entropy. So if the entropy is less than zero, that means it's going to be more ordered. Whereas if the entropy is greater than zero, you're going to get more disorder and more, randomness, if you want to put it that way. So if we take a look then at our first question, question 102, it says, for the change that occurs when steam condenses. Let's just think about this logically without even, in my toolbar here, without even looking at the options presented. If we can just take a look here. So steam. So if steam is going to condense, remember steam is a gas. So steam is a gas, liquid, or let's say water is a liquid. So think about it logically. Let's think about it in terms of, say, enthalpy and then entropy. So enthalpy, is it going to be exothermic or endothermic? Well, steam is a gas and they're very high volatile particles flying around very fast, very high energy. So if we want to turn it into a, say, condense it into a liquid or to water, it means that it has to slow down. The particles have to slow down. They have to lose their energy to turn into water, because water is a liquid, it's more ordered. So obviously what's more ordered than water is going to be a solid. So let's say if it turns into ice. But you can see that to turn a gas into liquid, you have to lose energy. And remember, if we're losing energy, that means our enthalpy, our internal energy, is going to go down because we're losing the internal energy. So that means our enthalpy is going to be less than 0, and it's an exothermic reaction. Now let's think about it in terms of entropy. So is it going to be more ordered or disordered if it goes from a gas to a liquid? Well, it's going to be a lot more ordered because they're going to be packed more tightly in a liquid, and it's going to be less chaos or less, let's put it this way, in a gas it's all over the place, whereas a liquid is more ordered. So you know that therefore the entropy, so if it's more disorder, it's going to be greater than 0. If it's less disorder, so if it's a more organized structure, the entropy is going to be less than 0. So you can see, therefore, without even looking at the options, you know that for a change to occur when steam condenses, it has to have a negative entropy and a negative enthalpy. So it's going to be exothermic. So therefore, your answer for 102 has to be B. So if we move on to question 103 now, it asks, the oxidation of mercury can be expressed by that equation. This reaction may occur spontaneously when. So let's write it out here. So we've got our Gibbs free energy equals our change in enthalpy minus temperature change in entropy. So before we even jump into the options again, just read the equation. You can do this in your spare time for every other equation just to make sure that you understand. You have a liquid and a gas that's forming a solid. So you know straight away it's going from more disorder into something very ordered that's a solid. So you know the entropy, S, is going to be less than 0. You know straight away. And we can see that in order for our gas or liquid to turn into a solid, we have to lose energy. Remember, it's moving from a very high energized particles in a gas or in a liquid to a stiff, not moving solid. So that means you have to lose energy. So you know, therefore, that your enthalpy, again, is going to be less than 0. So it's going to be an exothermic reaction. So these are the things you have to think about before you dive into these questions. Obviously not in the GAMSAT because you don't have time, but if you're preparing for the GAMSAT, think about this because it hones in the idea about Gibbs free energy, enthalpy, entropy, and this idea of thermodynamics and what we're talking about. So if we write out the numbers here, we've got so our exothermic reaction, we've got negative 91 kilojoules, again, because we're releasing heat. So let's write it in joules here, because our entropy is represented as joules per Kelvin. So it's going to be change in G equals minus 91. It's going to be 3 zeros, so joules, minus temperature, bracket, minus 172. So remember, again, it's going to be a not so spontaneous. So that's why S is less than 0. Joule Kelvin minus 1. So straight away, just by looking at this reaction, we know that for spontaneous reactions, G has to be less than 0. So for it to occur spontaneously, and this is what we're alluding to in the intro, temperature plays a massive fact or a massive role in whether a reaction is going to be spontaneous. And it makes sense. The heat of the system is going to determine whether the reaction is going to be spontaneous or not. And it makes a lot of sense. So if you think about it logically. So you can see that obviously for it to be spontaneous, this has to be less than 0. So this side has to be less than 91,000 joules. So this side, has to equal, less than 91,000 to be spontaneous. So therefore, the answer for 103 has to be that. So the only way we can do that is if we have T that is a value that's less than the specific maximum temperature value. So the answer for 103, therefore, has to be D. So if you're wondering what the actual value is, so T must not exceed 530 Kelvin. I mean, you can plug it into your calculator. It's not necessary to know to answer this question. But if you have a temperature more than 530 Kelvin, the reaction won't produce in a spontaneous manner. So that's the answer for D. I mean, if you still have more questions to this unit, or if you want to comment more about thermodynamics, you can post them in the comment section below, or you can contact us directly. We'd love to help. Thanks for your time. Bye now.